Okay, so today we're really getting down to brass tacks. Like, how do computers and circuits, all that digital stuff, actually work?
Right to the core.
Yeah, and you mentioned wanting to really understand the fundamentals, and I think this deep dive is perfect for that.
It is. It is.
We're going to be looking at logic and computer design fundamentals. Pulling out the essentials, no fluff. Think of it like...
Like getting the cheat codes.
Exactly, cheat codes to understanding your tech. Our mission here is to show you just how simple the ideas behind all this complicated technology really are.
It's surprisingly simple, and once you get these core ideas, it really unlocks an understanding of both the amazing power of these systems and their inherent limitations.
I mean, it all starts with the word digital, right?
Right.
And it's funny because it came from digital computers.
Yeah.
These were first used for calculations using distinct numbers, digits, like you see on your phone.
Mm-hmm.
But it didn't take long for digital to expand. Now it includes logic circuits or anything using separate, distinct pieces of information.
Anything that can be broken down into discrete states.
Right. And these logic circuits, what's really interesting is they only work with two states.
Just two.
True, which we represent as 1, and false, which we represent as 0.
The foundation of everything.
Yeah. And today, honestly, digital circuits, logic circuits, they're basically the same thing.
Essentially.
Yeah. And this whole idea of just two states, true and false, 1 and 0, that's it. That's the bedrock.
It really is. No matter how complex things get, it all boils down to manipulating those two states.
And then we have the general-purpose digital computer. This thing is incredible. A machine that follows a stored set of instructions, a program to work on data. What makes it so cool, so versatile, is that you can change the program and the data. So one piece of hardware could be used for, I don't know, anything, writing an email, designing a building.
The stored program concept, I think, is truly revolutionary because the same hardware can do radically different things.
Just by loading a different set of instructions.
Exactly. And that's a huge part of why the digital revolution took off.
It's crazy, yeah. But how do these systems, deal with the world around us?
Ah, yes.
Because the physical world, it's full of continuous stuff, like the exact weight of something or the precise temperature. It can be anything within a range. But then we, as humans, also use a lot of discrete data, like the numbers in our bank accounts or the letters in a document. So how do information systems bridge that gap?
Well, those continuous physical quantities, like temperature or light, can be represented by continuous electrical voltages, analog signals. Think of like a dimmer switch smoothly changing the brightness of a light.
Got it.
But you can also represent that brightness with a voltage that only takes on specific, limited values, and that's a digital signal.
Okay.
Now, here's where it gets interesting. These discrete values in the digital signals can be further broken down into multiple signals, each with only two possible values, binary.
Right, binary. The core of digital systems.
Absolutely. Most modern systems use these binary signals, 0 and 1. They're often represented by voltage ranges, high for 1, low for 0. But here's the thing. The voltages themselves are still analog. We just interpret them as binary if they fall within certain defined ranges.
So it's analog underneath, but we think about it as binary.
It is, and this approach is actually quite clever. By defining clear bands for high and low, we're building in a buffer against those little fluctuations, the noise, in electrical circuits.
Like, as long as the voltage is clearly in the high range or the low range, it doesn't matter the exact value.
Exactly. It gets interpreted as a 0 or a 1 correctly. It's a wide margin for error. And for consistent operation, that's huge.
It's like having, I don't know, two really big parking spaces.
Yeah.
If your car is clearly in one or the other, there's no confusion.
Right.
But why just two? Why not, say, 10 distinct voltage levels? We could directly represent our decimal digits.
Think about trying to have 10 distinct voltage levels to represent 0 through 9. You'd be dividing the voltage range into tiny slices. Any noise, any variation in the components could easily push a signal into the wrong level, causing errors.
So unreliable.
Exactly. A nightmare to design.
So binary, just two well-separated ranges, high and low, makes it so much simpler, more dependable.
Much more.
Less room for errors.
The book emphasizes that this reliability is absolutely key for computers to be accurate.
The simplicity of binary is actually its strength.
Precisely. These circuits are easier to design, to manufacture, and the calculations, they're repeatable. Same input, same output, every time.
Consistent.
That's fundamental. Not as easy with more complex systems.
Okay, so we have this binary information. What about the computer itself? What are the pieces inside?
All right, at a high level, you've got memory.
Okay.
This is where the programs and the data live. Then you have the data path, where the actual processing happens, arithmetic, logic, all that. And finally, the control unit.
What does the control unit do?
Think of it as the conductor of an orchestra. It directs the flow of information, telling the other components what to do.
I like that analogy.
The data path and control unit together, that's your CPU. The brain.
The CPU. And then we have input devices like keyboards and output devices like monitors.
Right, to get information in and out.
And it's amazing the variety of devices we can connect. Cameras, network cards.
It is, all communicating using these same digital principles, even if they have analog parts in how they interact with the physical world.
Oh, that's interesting. So it's not like a clean separation.
Not always. There's that interface between the digital world of the computer and our analog world. That's a whole other topic.
Okay, maybe for another deep dive. But back to the CPU. You said the control unit fetches instructions from memory.
It does, one after the other, then it signals the data path to perform those instructions.
Got it.
So both the instructions, the software, and the data, they're in the same memory.
Altogether.
Very efficient, very flexible design.
Now, when we think digital systems, most people jump to PCs. But the book mentions there's a whole world beyond that, right?
Oh, absolutely. PCs are powerful, but smaller single-chip computers, microcontrollers, they're everywhere. And specialized processors like DSPs, digital signal processors, they're even more common. These are the hidden brains in so many devices, performing specific tasks.
Often with no human interaction at all.
Right.
We're talking embedded systems, right?
Exactly. Integral parts of other products. You don't see them, but they're there.
Like in your smartphone, your car, even a microwave.
Oh, absolutely. They're all over, managing everything from airbags to, like you said, the display on your microwave.
It's mind-blowing how many there are. And to really show how this digital and analog stuff intertwines, the book gives a great example, a wireless weather station.
Oh, yes.
Walk us through how that works.
Okay, so the outdoor unit, it has a thermistor. This is a type of resistor, and its resistance changes with temperature.
So it's measuring the temperature.
It is. That's an analog measurement. Now, a circuit converts this changing resistance into a corresponding analog voltage.
Still continuous.
Still continuous. Now, this voltage goes into an AD converter, an analog to digital converter.
Okay.
This chip, it takes that continuous voltage and turns it into a digital number. Binary, usually.
So the smooth temperature reading becomes a series of distinct digital values.
Exactly. If the AD converter has 8 bits of resolution, it might divide the temperature range into 256 distinct values.
Interesting.
This process going from continuous to discrete, that's called quantization. And there's a tiny bit of error there, quantization error, because a single digital value represents a small range of temperatures.
The more bits, the more precise.
Right. Smaller steps, higher precision. And then this digital temperature reading, it gets transmitted wirelessly to the indoor base station.
Okay. What happens there?
Well, the base station gets this digital data. Its microcontroller might do some processing, maybe calibrate the reading or format it nicely. Now, if the base station has an old-style analog meter with a needle, it needs to go back the other way. Convert the digital number back into an analog voltage.
Using a DA converter.
Exactly, a digital to analog converter. This produces voltage levels that try to approximate the original analog signal.
Cool.
Often you'll have extra circuitry to smooth those voltage levels, make it more continuous for the meter.
So it goes analog, digital, then potentially back to analog?
It's a full circle.
Wow. So these systems, they can have billions of transistors. How do engineers even start to design something that complex?
That's where layers of abstraction come in. Super important idea in computer system design.
What does that mean?
Well, instead of thinking about every single transistor, designers work at a higher level. They describe the system using bigger functional blocks.
Got it.
Each block can then be designed separately, and the complex details inside are hidden.
It's like building a house. You don't start with atoms, you start with rooms.
Exactly. Walls, roofs, doors, each made of smaller things, but you manage the overall design at a higher level. Each layer hides the complexity below it.
That makes sense.
Like when you write code in Python or Java, you're at a very high level of abstraction. You're thinking about the logic of the program. You don't need to know the exact instructions the processor will execute.
Or how the electrons are moving in the transistors.
Right. All that complexity is handled by the layers below. That's what makes designing these systems even possible.
So there's a whole stack of these abstraction layers, from the problem down to the physical circuits. Can you give us a quick tour?
Sure. At the very top, you have the algorithm, the steps to solve the problem.
Okay.
This is translated into a program in a high-level language. When it runs, it interacts with the operating system, the OS.
Which manages the computer's resources.
Right. Both the program and the OS, they're ultimately translated into instructions for the specific processor, the instruction set architecture.
Got it.
The hardware implementation of that architecture, the way the processor actually carries out those instructions, that's the microarchitecture. Below that, you have register transfers, how data moves between the processor's storage units. then logic gates, which do basic operations on bits, and finally, the transistor circuits that implement those logic gates.
So many layers.
It's a lot. But the beauty is you can often change things at a lower level without redesigning everything above it.
Like a chip manufacturer could make a faster processor that still understands the same instructions.
Exactly. Your existing software runs faster without changes.
Innovation and compatibility.
That's the power of abstraction.
So what about designing a digital system from scratch? What are the steps?
Well, it starts with a clear problem definition. What does the system need to do? Then you come up with a solution, often using algorithms or diagrams.
Okay.
You refine and optimize that solution, taking into account things like performance, cost, power consumption.
Makes sense.
Then there's technology mapping. You figure out how to build it using specific components. And finally, you verify, you test, you make sure it works as intended.
So it's systematic but also iterative.
Definitely. You often go back and forth, refining the design as you go.
Now, we know digital systems use binary, but we think in decimal, and then there's all hexadecimal. Why so many number systems?
Well, binary is great for computers, but writing long strings of zeros and ones, it's not very human-friendly.
It gets messy.
It does. Octal, base 8, and hexadecimal, base 16, they're essentially shorthands for binary. And the reason they work so well is because their bases are powers of 2.
Oh, okay.
8 is 2 cubed, and 16 is 2 to the 4th power. So each octal digit represents 3 binary digits. Each hexadecimal digit represents 4.
So you can group the binary digits and make them much easier to read.
Exactly. Instead of, say, 11010110010, which is a mouthful, you can group it and write it as 26710 in octal or B72 in hexadecimal. Much more compact.
Definitely easier on the eyes. Now, let's break down binary numbers a bit more. It's base 2, so only 0 and 1. How do we relate those to our decimal numbers?
Each position in a binary number represents a power of 2. Starting from the rightmost digit, that's 2 to the 0th power, then 2 to the first, 2 squared, and so on.
So to convert to decimal, you look at each position with a 1, calculate the power of 2, and add them up.
Precisely. For example, 1,110 in binary would be 16 plus 4 plus 2, which is 22 in decimal.
Got it. And each of those zeros and ones, that's a bit, right? Short for binary digit.
That's right. And when we talk about memory, storage, data rates, we often use prefixes like kilo, mega, giga, tara.
Okay.
In the context of powers of 2, a kilobyte is typically 2 to the 10th bytes, a megabyte 2 to the 20th, and so on. But be careful, sometimes those prefixes are used in their decimal meaning, powers of 10.
Ah, so you have to pay attention to the context.
You do, especially with storage devices where marketing can get a bit creative.
Right. Now, how do you go the other way? Decimal to binary.
One common method is successive division. You divide the decimal number by 2 repeatedly and keep track of the remainders. Then you read the remainders in reverse order.
Like a little puzzle.
It is, kind of. So for 26, you'd get remainders of 0, 1, 0, 1, 1. Read that backwards, you get 1110, the binary equivalent of 26.
Neat. And you mentioned octal and hexadecimal as binary shorthands. Can you give us an example of how to convert between them?
Let's take that long binary number again, 101011101010. For octal, you group the digits into threes, starting from the right. Add leading zeros if you need to, so we get 010, 110, 111, 001, and then just a 0 at the end. You convert each group to its octal equivalent, 2, 6, 7, 1, and 0. So the octal representation is 2, 6, 7, 10. For hexadecimal, you group into fours, again, starting from the right, adding leading zeros if needed. We get 10, 11, 0, 1, 1, 1, 0, 0, 10. Convert each group to its hex equivalent, B7, 2. So the hex representation is B72.
Much more manageable.
It is.
Now, with digital systems, there's a limit to how big a number you can represent, right?
Absolutely. It depends on how many bits the hardware uses. For an 8-bit unsigned integer, you have 8 binary digits. That means you can represent 2 to the 8th power, which is 256 different values.
So from 0 to 255.
Right. More bits, wider range. A 32-bit integer can represent values up to over 4 billion.
So the number of bits is really important. What about arithmetic? How do you do addition, subtraction, multiplication in binary?
The rules are similar to decimal, but you only have 0 and 1. And in binary addition, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0 with a carry of 1.
Just like carrying over a 10 in decimal addition.
Exactly. Subtraction is similar, with borrowing when you need to subtract from 0. And multiplication is actually kind of simpler because you're only multiplying by 0 or 1.
So the partial products are either 0 or a copy of the other number.
Right. Then you add those up according to their place values. For octal and hexadecimal, you can convert to decimal, do the calculation, and convert back. Or you can learn the specific rules for those bases.
Decimal conversion sounds easier.
Usually it is.
What about converting between decimal and any other base?
To convert from another base to decimal, you use the positional values. Each digit is multiplied by the base raised to the power of its position, starting from 0 for the rightmost digit. Then you add those up.
Okay.
To convert a decimal to another base, for integers, you repeatedly divide by the base and keep track of the remainders. The remainders, in reverse order, give you the new representation.
And for fractions?
You multiply by the base repeatedly and keep track of the integer parts. Those, in forward order, form the fractional part in the new base.
So we use decimal, computers use binary. How do we represent decimal digits using binary code?
That's where BCD comes in, binary coded decimal. Each decimal digit from 0 to 9 is represented by a 4-bit binary code.
So for example, the decimal number 295 would be 0010100101 in BCD.
Exactly. You just replace each decimal digit with its 4-bit code. But it's important to remember that BCD is not the same as the direct binary representation for values greater than 9.
Right. 15 in BCD is 00010101, but in straight binary it's 1111.
Exactly. BCD uses more bits, but it's easier to convert between decimal and binary, which can be useful for things like displays.
Now what about text? We need to represent letters and symbols too.
Right. That's where alphanumeric codes come in. ASCII, the American Standard Code for Information Interchange, is a 7-bit code.
7 bits.
Yes. It can represent 128 different characters, letters, numbers, punctuation, some control characters.
And since computers use 8-bit bytes, that extra bit is often 0 or sometimes used for additional characters.
Right. But ASCII is limited to mostly English characters. That's where Unicode comes in.
The universal standard.
Exactly. It aims to have a code for every character in every writing system.
Wow.
Encodings like UTS-8 are used to represent these Unicode characters. It's variable length, but it's compatible with ASCII for the first 128 characters.
Clever. Now, how do we make sure data doesn't get corrupted during transmission?
One simple method is using a parity bit. This is an extra bit added to a code word. It's set so that the total number of ones is either even or odd. Then, when the data is received, the parity is checked. If it doesn't match, you know there's been an error.
A basic error detection mechanism.
It is. And finally, there are gray codes.
What are those used for?
They have a special property where only 1 bit changes between consecutive values. This makes them great for things like optical shaft encoders that measure rotation.
Why is that?
In a normal binary code, multiple bits can change at once. If the sensor is right at the transition point, you can get weird readings. But with the gray code, only 1 bit flips, so it's much smoother, no ambiguity.
So they're used for specific applications.
They are. They also have advantages in low-power circuits.
Well, this has been a really in-depth look at the fundamentals of digital systems.
We've covered a lot. Binary, computer architecture, abstraction, number systems, codes.
It's incredible to think that this simple idea of using just 2 states, 0 and 1, has led to such complex and versatile technology. It really makes you wonder, are there other ways to do computing? What would those look like? What limitations would they have?
That's a question worth pondering.
It is. For now, we hope you have a better understanding of how the digital world works from the ground up. And if you have any questions, please reach out. We love to dig deeper.
We do.
Until next time.